All right, welcome. Good afternoon, good evening. Thanks for joining us today for our final back to school webinar of this year, Reimagining Chemistry with OpenSciEd. How are familiar chemistry topics addressed? My name is Erica Palis with OpenSciEd, and I'm joined today by Michael Novak and Nicole Vick from Northwestern. Nicole dropped the slides in the chat if you're interested in referencing the PDF of that. And we'll have a few other things popping up in the chat throughout today as examples and things of that nature if you would wish to view them. We'd love to know who's here. So if you get a second in the chat, if you can drop your name, maybe your role and location. It could be as simple as a state. And if you're a teacher, if you're in some other role in education. And then maybe what you're hoping to learn today. So what interested you about this topic when you saw it on the website? What are you hoping to get out of it? And that'll just help us get an idea of who's in the room and if there are specific things we should spend some extra time on today based on who's here. So give everyone a second to do that as we're letting a few more people in. All right, go ahead and keep adding those and we'll keep moving on. All right, so what are we going to talk about today? Sort of three things that we're going to cover in this webinar. We're going to talk about where the traditional topics live in OpenSciEd chemistry and quote unquote traditional. So we've used the word familiar to think about some of the things that we've maybe typically seen in other chemistry materials or that we're used to teaching. And we'll identify sort of where they show up within OpenSciEd's chemistry course. We'll also look at how OpenSciEd chemistry is different in its approach to some of those topics specifically. And then we'll kind of end by thinking through what rigor means and how OpenSciEd delivers rigor and what rigor looks like in OpenSciEd's chemistry model. Let's start with a little bit of background on OpenSciEd as an organization, just so we're all sort of on the same page around what OpenSciEd is and who we are. OpenSciEd is a nonprofit organization. So we have a small staff of people as part of OpenSciEd as an organization, but together we bring together many different people in order to make the materials a reality and in order to support schools, teachers, districts with use of these materials. And so sort of thinking about that in four groups. The first is world-class curriculum developers. So Nicole and Michael are here today from Northwestern University, who is part of the development consortium for our high school materials. So those are the organizations, the people, the universities that actually write and create the curricular materials that you utilize in your classrooms. The second is state science administrators. So throughout the development of all of our curricula from elementary through high school, we have a robust field test process. And as part of that process, we have 10 partner states. And from those 10 states, multiple representatives from that state that help to guide decisions in the development process and also to help organize and run the field testing of the materials in those 10 states. And so that's where teachers come in terms of the development of OpenSciEd's materials. In those 10 states, the entire curricula is taught in its entirety from the first lesson to the end before it's even released to the public. So we have hundreds of teachers and thousands of students that are using these materials in their classrooms. They're collecting feedback and data, they're providing that back to the developers, and then we're revising these units before they're released publicly. And then lastly, we are a nonprofit, and we can only make these materials and offer them for free through philanthropic funding and the generous organizations that support this work. And so through these partnerships, we create free, high-quality NGSS-aligned science instructional materials, and we also have professional learning experiences that we provide in support of them for teachers. An update on our high school materials. They were recently submitted and reviewed by EdReports. And so all three of our high school courses have received an all green rating from EdReports. If you're interested in reviewing those reviews and reading through them, we'll drop the link in the chat. Maybe Nicole could do that for me. But there are three sort of criteria for EdReports designed for the NGSS: coherence and scope and usability. And so the materials are evaluated against a series of criteria in those three categories. and rated with a score. And so if you're interested in reading those, our chemistry course was the first course to receive an all green, first chemistry course to receive an all green rating by Ed Reports. All right, so that's a little bit about OpenSciEd. Now let's talk about our chemistry course a little bit specifically. We're going to dive deeper into chemistry today. That's our focus. And so just as setting the groundwork, OpenSciEd's materials, not just chemistry, but all of them, are designed to address the framework for K-12 science education and the next generation science standards. So that is our baseline, right? That's what we're attending to when we're making decisions around what to teach and how. Our design specifications, so the things that guide the development of all of our materials, really define how the guidance and goals of the framework could look in real classrooms, right? So taking that guidance and turning it into a reality is what our work entails when developing materials. Another important factor, and I think many of us are aware of this if you're familiar with the materials, is that all of the high school performance expectations are addressed throughout the 3 courses. So that means the physical science, the life science, as well as the earth, space, and engineering are integrated across those 3 courses, biology, chemistry, and physics. So a few key things that are really pivotal to OpenSciEd's materials and what makes us different and the why as to why we abide by those things. The first is that our materials are phenomena driven and have a storyline instructional material, a coherent storyline. And so we believe that, and research shows that students learn best when ideas are connected to real problems and they're revisited over time. And so every single unit in our materials is based in a phenomena, and we use student ideas and questions to really drive the storyline and how we make sense of that phenomena throughout the unit. Interdisciplinary connections, like we mentioned on the previous slide briefly. So our units, our courses integrate the earth, space, and engineering standards as well. And the big reason for this is that, our biggest challenges today are real problems, which is what we want students to be able to be thinking about and solving as they go out into the world, require a lot more than just chemistry, right? They require chemistry plus other sciences. So if we think about climate and energy, by integrating these earth, space, and engineering standards, we really are able to show students how chemistry and why chemistry matters and how it connects to real world problems and problem solving. Third is authentic investigations in labs. So we want to think about lab investigations as their purpose is to figure out ideas and science ideas, not just confirming something that they've already learned. And so students are really thinking and working like scientists through authentic investigations. They're critiquing experimental procedures and critiquing results rather than just be following an instructional set of steps. Fourth, discussion and argumentation is really pivotal to our materials and the design of our materials. We believe that sense making is social. So explaining and defending ideas with evidence, this is a really important skill. And we believe it's an important skill for all students, not just to have a place in maybe a higher seminar type course, but in all levels of science. And then lastly, math and science in service of figuring out. And so we use math in our materials as a tool for making sense of phenomena. So there's conceptual understanding that's built first, and then that's transferred into this quantitative reasoning. So we're using the math to figure something out that's conceptual. Okay, so this approach, those kind of key 5 things, some might be similar to things you already do, some might be a little bit different. And so, but it often leads to common questions that we hear when people start using our materials for the first time or integrating some different practices into their classroom. And so some of those are, where are the traditional topics, right? It looks a little bit different. It's hard for me to identify some of the things I've typically taught, like where are they in here? And then second, why does it look different than a traditional course? What's the reason for this? And then third, will this prepare students for advanced courses in college, right? Where's the evidence? How do I know? Will this get my students to where they need to be next? So we're going to look at those 3 today, and we'll start with that first one of just sort of identifying where these topics that are typical to a chemistry course show up. So thinking about what those topics are when we're talking about familiar chemistry topics in the high school chemistry course. we're going to use the ACS guidelines and recommendations to sort of formulate this list of key concepts. So the ACS identifies key concepts every chemistry course should address, but they don't prescribe an order for teaching them. So we're going to think about a little bit, like, how do we currently, and how does OpenSciEd sequence these ideas for meaningful learning? So we're going to drop a Padlet in the chat. And I'd invite everyone to open it up. Nicole, can you do that for me? Thank you. So on this Padlet that we're about to put in the chat, you're going to see, oh, it's in there. You're going to see this list of topics that the ACS guidelines outline. You'll see atomic structure, chemical changes, some of these familiar chemistry topics. And what I'd like you to do is when you go into that Padlet, and you'll see the directions in the chat, is read through them, read through these different topics that you're probably familiar with, and 1-star rate the ones that you think are important for high school chemistry. Okay, so you'll give 1-star rating to the ones that you think are important. You can rate as many as you want. And then you're going to give 5 stars, so then maybe review them one more time after you've rated them all with 1 stars. Go back and change your rating to 5 stars to topics that are important and should be addressed in the first few months of school. Pick 5 topics. So rate all of them if you think they're important, give them a star, and then pick the 5 that you would start the year with. Which are the 5 you would teach first? Okay, if you've made your ratings, I'd love to hear. There's a third question. You could drop it in the chat. Like, how or why did you choose your 5 start of the year topics? Just in like one sentence or so, like, how did you pick the 5 that you picked? What are you basing that on? What are your reasons for picking those 5? Got some ideas in the chat. Rory and Emma are saying they think that the other concepts will build on those. Okay, so I'm setting a foundation. Great. So a couple of takeaways from looking at this list, like on our Padlet. First is like, we don't all agree, right? Some of us maybe teach different things at different times. We didn't have any that had 5 stars, 100%. Atomic structure got pretty close, but we have differences in terms of who is teaching what maybe first and what they would start with. So that's interesting, right? We mentioned on the previous slide that the ACS doesn't necessarily recommend an order at which we teach those. On this slide, I'll show how OpenSciEd starts the year. We have some others too that we'll see another representation of this soon, but these are like sort of the 5 that might get the 5-star rating: states of matter, physical changes, nature of science, quantitative analysis, and thermodynamics. And so some similarities with some of our top 5 in this group as well, and some differences. And so let's think about where those topics show up in the materials and across the OpenSciEd's chemistry course. And so for some framing, OpenSciEd's chemistry course has 5 units. This is the entire high school scope and sequence up here on the slide. And you'll see the 5 chemistry courses in the middle. And a couple of things to note here is these units are building off of one another, and not just within chemistry as represented by these arrows, but across the entire course. So there are connections between biology and chemistry and physics courses, the physics course as well. You'll also see the representation of the integrated standards, like we mentioned. So in physics and chemistry, the physical science PEs are distributed across those 2 courses. And then we have those earth, space, and engineering standards integrated as well. You'll also notice that you'll see the asterisk here represents that ideas within that standard are built across multiple units. So just because a standard is listed in one unit, that doesn't mean that it's the only place it's being addressed, but we're building some ideas in one unit and additional ideas as part of that standard in another. Oh, some examples there. And so if we look at this is another kind of representation of where those topics that we saw in that Padlet show up and compared to maybe a traditional textbook order. So if you're thinking about a textbook where we're divided by topical chapters, it might follow an order similar to what we see on the left. And then if we think of OpenSciEd's approach, OpenSciEd has a phenomena-based spiral. So instead of a topical structure, the structure is based on the phenomena and the standards that make sense to build and the ideas that make sense to build in the context of that phenomena. So as some examples, like we'll see asterisk or emojis that maybe show up once over here are showing up multiple times in this representation of OpenSciEd's phenomena-based spiral on the right. And so how we discuss and what we're learning about in relation to atomic structure in one unit will look different than how we're learning about it and the ideas we're building in another unit. Another representation of that is this table, which we'll drop in the chat towards the end of the presentation today, or you can reference this again later. But it has the 5 units down the left and then those topics we saw across the top. And you can see where they are addressed across each unit, and most of them are being addressed multiple times in multiple units. Okay. So now we have this high-level view of where these familiar topics are occurring within the materials. We're going to dive deeper into 4 specific examples from that list and see how they are, how OpenSciEd approaches student learning and why we do it that way within the actual lessons and some unit examples. So we're going to look at atomic structure, naming compounds, stoichiometry, and gas laws today and see some specific examples of how those build across the curriculum. And I'm going to pass it to Michael.
Thanks, Erica. And I know you'll still be driving slides, so thank you for that. I'll cue you as best as I can for each. But atomic structure is so interesting because I was thinking about what we just saw in the data we collected from our community here on Zoom tonight. It was our top item, and it was stood out, therefore, as one of the first things that we traditionally teach. And many of us think is important to kind of get under our belt right away for students. And the ACS also calls it out as, one of the first traditional topics that sometimes is taught in textbooks. But again, there's no prescribed order. So where do we dig into atomic structure in the course? Well, let's take a look at that. Because the first unit where we really start to dig into atomic structure beyond the middle school level is the second unit. The first unit stays focused on kind of a states of matter model for particles, which at an atom or molecular level really goes no further than Dalton did in the 1820s. It's this unit, C2, the second unit, that really pushes us to go beyond what the disciplinary core ideas call for about understanding particles in middle school to understand what's inside of an atom. And what is it about this unit and the phenomena that kids explore that motivate that? Well, the question we're trying to figure out, the anchoring phenomena, is built around trying to figure out what's happening with lightning, what causes it, why are someplace safer than others when it strikes. And as just beginning to investigate that phenomena leads us to a variety of related phenomena that students are familiar with, such as static electricity interactions, electricity from the wall, and just the whole space of electrical interactions. What kind of motivates really what's thinking about what is happening at a particle level that requires us to go deeper than just atoms are like spheres. They connect together with other atoms to make compounds, and those kind of particles can bounce off each other. So it's the second unit that we start to go a little deeper into atomic structure, and it motivates the development of what we call the paperclip model of atomic structure. And Erica, if you wouldn't mind sharing that, I'll unblur too as we do this next part. I've actually built some of those paperclip models here. Sort of about the 5th lesson of that unit, we realize we need a way to start accounting for something in lightning that we actually simulate and observe in our classroom. We need to account for something in static electricity. And one common phenomena that students explore in lesson 4 is to like take two pieces of tape, pull them apart, and then realize, geez, these things tend to be attracted together or repel, depending on which piece of tape I use. And it's lesson 5 where we really start to understand and realize that atoms are actually made of smaller parts. Some of these are referred to as negative parts or electrons, some are referred to as positive or protons, and some are neutral or neutrons. And some of them are in a nucleus and some are around the outside of the atom. This model that we build of here's two atoms of the same substance allows us to explain a lot of macroscopic phenomena, such as why is it when I rub two pieces of tape together, they might be attracted to each other, or why might they repel? Well, actually, working with this manipulative, I don't know if you can see my screen here, we do things like actually rub the two pieces together and realize, wait, I just changed the net charge on this one to have 3 positives and 2 negatives, and this one now has 4 negatives and 3 positives. Wait, I have 2 atoms now that have different net charge. Could that explain whether things attract or repulse in all these phenomena? Turns out it does. And continuing to use the electron manipulative, this teeny little paper clip that sticks to many things, connects things together, and even looks like a little minus sign, ends up being something we build throughout the unit and will continue to carry into the 3rd unit of the course. And let's show some examples of what we can do with this paperclip model. That still isn't the full atomic structure we're going to get to in the course, but it's a step deeper than our middle school model. Well, one thing we can do is we can start thinking about, well, what happens if you can you have a neutral atom or molecule, you start pushing electrons to one side of it. Well, that allows us to develop the idea molecules like water can have polarity. Must be that the electrons in it are shifted to one side. We can go a step further for that, not just account for water, but things like salt in water, which ends up being a great conductor of electricity. And part of that model to develop that is there's these shifted electrons can shift so much that one particle loses an electron and one gains an electron. Well, then we should name those. We should call those things that have a net charge, and we start to identify those as ions. Notice though, with this model, we're still not at the level of deeper atomic structure that one might associate with the periodic table. But we've made some incremental progress on our model from middle school. So where does atomic structure then get developed further in our course? Erica, could you go to our next slide? Well, we're just in C2 right now, right? This is what we just summarized. The line above kind of says, hey, C1, our first unit, those 2 models up there, particles are in motion, they collide. Matter can be made of atoms and molecules. We figured that out in middle school. There's a lot of high school level practices and energy related ideas we can develop with that too. But to explain ice, water, and air things happening on the Earth's surface doesn't require us to go any deeper. It's lightning that requires us to realize, wait, our model of particles is not sufficient. There must be something inside them that's causing things to repel and attract, and that's these things that hold charge. They allow us to explain why molecules can have polarity and atoms or molecules can have a net charge, be an ion. Notice there's more to the course though. So let's see where the model of matter gets refined in our next unit. Sorry, I forgot a slide in between there. I'd like to point out something else that happens in the 2nd unit. We're starting to realize there are force interactions in systems like lightning from a cloud, or the simulated lightning in the classroom, or static electricity, or a variety of other things that students investigate in this unit. And it is the bottom corner of this diagram, force interactions, that get introduced in this unit, whereas prior unit, C1, really focused on just matter and energy. It's the force interactions that beg explanation for why we need to go deeper in terms of that top left corner of just saying matter is made of particles. Well, what kind of particles could be causing force interactions? We never really had that need in middle school. but we do now in the second unit. This anchor chart ends up framing the entire course and motivates a conceptual way of thinking about chemistry, not just from matter structure, not just from energy transfers, but deep thinking about force interactions and fields generated by particles to account for a variety of phenomena. Those traditionally maybe that fall under what we would expect to see in a chemistry class, and those that are outside in the world in an earth science context. So let's take a look at, though, how that matter model gets refined further. The atomic structure, we're not done with. Our third unit, which is centered around some future thinking that is in the works, both in our country and the larger world, is moving towards thinking about like setting up permanent or semi-permanent bases on the moon as a stepping stone to other parts of our solar system to try to figure out the science necessary to work and live beyond Earth. And as they claim, anything we do in that space also is going to inform maybe how we could live on Earth more sustainably. Because trying to figure out how to live and work in space, places like the moon and beyond, it's going to require us to not ship everything there. The things we need, we're going to either have to find or make or recycle. And so thinking about what are those things, what are their bulk properties, how would we even find them on a planetary surface, motivates a lot of like what makes something sticky or what makes something flow over a rock surface or wedge between two solids and crack it apart, because those might be clues for where we would find water or the gases we need like oxygen. And whenever we find the raw materials that we might be able to build stuff out of, we're going to have to understand how you can put different atoms together. So examining molecular structure and atomic structure comes out of sort of trying to understand why is it you can put certain things like carbon together with four other atoms over and over, but other things you can't? What's going on inside the atom that would explain that? So it's in this unit we start to compare multiple molecular and atomic models. And on our next slide, Erica, you can see we still start with the paperclip model. It's very useful. But we see simulations where like, geez, those paper clips that kind of like move all around. They kind of float around in a cloud. And then other models like, well, we could also think of like some being far away from the nucleus and some being further in, like in different shells. Ultimately, this leads us to, though, realizing the thing we need for explaining bonding really is just the outer electrons. Those are really the paper clips that join things together. And so it's at this point that we're set up to first build the periodic table ourselves to reflect the periodicity that this atomic structure begs connecting to. And then, Nicole, I know it's one of your favorite lessons. And then we use the periodic table going forward, of course, as a maybe intermediate or more refined version of what we built as a class. But here's where we would traditionally say we get to like pretty full atomic structure in terms of what might often be at the start of the year. Here we are midway through the year having developed that. So what makes me reflect on OpenSciEd's approach. We're not developing atomic structure soup to nuts as like the necessary level of depth for every phenomena. There's things we can explain at a macro scale where we don't have to go deeply into atomic structure. In fact, we start the year with that. And we only have to go so deep to explain certain phenomena. So we save it to kind of the middle of the course where we get to maybe the full atomic structure details that we might traditionally think, do we need to start the year with it? We'd argue, well, it depends what phenomena we're trying to explain. And it's only at this point that we feel like we have enough of phenomena that we need the full details of what's inside an atom. I'm going to pass it to you, Nicole, for the next part.
Oh. Well, we had a question come up from Chris in the chat that I think probably makes sense to talk about now before we move on to naming compounds of adding in forces of attractions into unit 1 to talk about the forces in solid and liquid particles and holding them together. So is it okay to add that in earlier, some of that forces thinking in that way into that first unit? And like what would kind of the possible trickle down effect be in unit 2 if that was done earlier?
Thanks for asking that question, Chris. Could we go back to that force matter energy triangle? This is a pretty complex triangle. Both our chemistry and physics course build this triangle out completely in Unit 2, but both courses only attack the first unit from a matter and energy perspective. We think that's sufficient number of lenses to try to explain phenomena, even in a physics class, which is another non-traditional approach. Wait, we're not going to introduce forces right away? No. We're going to account for where the energy is coming from and going to. We're going to track the particles always and come up with ways of how we know there's energy in the system, realizing the link between the two. Energy transfers and matter changes happen together. Not that you couldn't do it, but we just saw it as a useful lens to think about matter and energy first and foremost, because they'll have done that in so many middle school OpenSciEd units, whether it's an ecosystem or plate tectonics or hailstorm or chemical reactions in a made to ready to eat meal or sound moving through the air. Those two frames will be very useful to leverage, we think, as an entry-level experience for kids, and forces could be useful. It's just we kind of thought in OpenSciEd, it's just one too many perspectives. And when we get to it, we need kids reasoning about fields as well, a very abstract concept. And so what a field is, and that maybe you can store energy in the system when there's a field. We thought it was better to wait to Unit 2. But you do bring up a good point. Water's sticky. It attracts, it sticks to itself. Identifying that there's something going on there could be productive.
Okay, all right. Naming compounds. So one of like the big shifts with OpenSciEd is we don't explicitly teach the rules for naming compounds for both ionic and covalent compounds. So let's kind of think about how we're introducing them and the focus of really digging in and using patterns to have students start to make connections between chemical formulas and compound names. So Erica, if you want to go, thank you. So in our second unit, we start to do this early and we introduce students to the names and formulas of different ionic compounds or salts in a home learning reading that they get to think about, like, why do we need to get out of the water when lightning is in the area? And so for part of the reading, one thing that they are introduced to is an unfortunate incident that happened where there were a flock of geese in a pond and it got hit by lightning and the poor geese didn't make it. And they start to think about, like, okay, if I have like these salts, these dissolved substances in this water, these have charges to them. They are ions. So that's going to allow this electricity to move through. So we can see here some of the patterns that you might expect students to pull out of this is that the positively charged atom, so like sodium, potassium, or magnesium or calcium, gets its own name. Like the name of the element is the name of the salt, and that the negatively charged ion, like chlorine or fluorine or oxygen, has the ending changed to IDE. So rather us explicitly teaching that changing of it allows students to see that pattern of, oh, it's not sodium chlorine, it's sodium chloride, potassium chloride, sodium fluoride. Start to really emphasize those patterns in there, and students can take that moving forward into the next unit, which is C3. So we can go to our next slide, where we start off in lesson 1 with students looking at a whole list of reactants and products of these chemical processes that we need for life. So they revisit photosynthesis that they had first heard about in the biology program, and we start to develop models for those chemical reactions. So and we'll in a second here look at that handout for students to start to make those connections of how they're being rearranged, what are the patterns to the different types of atoms in there, and throughout the rest of the unit, students are exposed to more names and formulas of compounds. So let's take a moment to look at that example from lesson 1. So this is just part of some of those reactions that students see. So water electrolysis, they can start to see it's broken apart. We also are starting to see the ideas of thinking about conservation of matter and balancing reactions. So we can see we're starting to go inputs and outputs. So products and reactants move in there. We think about glass. We start to see polyatomic ions like carbonate and sodium carbonate. We start to see carbon dioxide and other atoms that are more covalently bonded. So this really gives students some space to start to like seed those ideas of continuing to be exposed to name of compounds, but then also starting to build in how chemicals react with each other, and we create new things. So let's continue on where we start to get even deeper into this, where we're developing these models for chemical reactions. We're starting to write chemical formulas and chemical reactions. We're working on balancing them. And we really start to consider, like, how do we explain some of these bulk matter properties and why one atom will split off of a chemical compound and reform with the new one. So we start to use electronegativity to really explain the differences between bond character. Like we've already got ionic bonds from C2, right? We have ionic compounds there, but not all compounds are the same. We have these other ones. So we start to really look more at a continuum versus a metal plus a nonmetal is an ionic compound, and two nonmetals are covalent compounds. Like they're not all created equal, and that's because of differences in electronegativity. So let's look at that on the next slide, the next couple of slides, actually. So students really start to think we've built that ionic bond character in C2. So this is really leveraging some of those ideas that they had, and they see that when we have differences in electronegativity that are not equal, we get a atom or a compound that is very ionic in its character. When we have electronegativity values that are equal, we get this truly covalent bond where they are equally sharing those valence electrons between them, and it's a little bit harder to break those bonds apart. So we also start to think about the shift of the electrons between the two. And on our next slide, we move a little bit forward from our paperclip model to start to use clothespins and ball and stick models to show those relative distances between the electrons that are being shared between atoms. And so we look at this, we start to evaluate our different models. You can see every time students are experiencing and seeing some sort of representation of a chemical formula, they have the name. And here we also give multiple different visual cues for students to look at throughout Unit 3. So where does this take us moving forward? So we continue throughout Units 3 and 4. And in Unit 5, we introduce hydrocarbons and start to think about naming of hydrocarbons and other carbon-based compounds. And we really examine bond strengths and bond energies through them using these magnetic marbles and steel marbles to help us explain how we can use chemistry to evaluate the fuels and transportation options to benefit Earth and our communities in the future. So let's see kind of where we end up with matter learning. So in C3, we've fully built out that atomic model. We've started to think about reactions. We're balancing those chemical reactions. We're predicting how the different chemicals that are taking place in the products will rearrange to form different, the reactants will rearrange to form different products. And then we continue to move forward in our story to where we end up with C5, where we start to bring in energy and what's the role of energy in those different chemical reactions. So to real quick kind of summarize our approach with naming compounds, we really want to look at those patterns within a meaningful context. So using that phenomenon-based thinking to support how we're thinking around naming chemical formulas and calling them out versus just spending time on teaching the rules, which we all know there are multiple exceptions to those rules that can get really confusing for our kiddos. So we try to avoid that categorization that these are the way that it works, and it's very regimental. So some of those things with naming compounds, and again, the foundations that we have built up in C1, C2, and C3 help support our next topic. So everybody's favorite in chemistry is stoichiometry. So let's go ahead to our next slide here. So in C1, we start off the year really scaffolding mathematical and computational thinking with unit conversions. So which we're using that language versus dimensional analysis to better match the language of NGSS, but also the language that students use in their math courses. So I would recommend speaking with your math teachers. What terminology do they use for unit conversions or dimensional analysis? And just matching those up helps kids use the same process between your math and science classes. We also work with powers of 10, both in C1, and we revisit them again in C2 as students develop Coulomb's law and work to mathematically develop that using experimental data. So let's go into C4. C4 is where we build out stoichiometry. So in C3, students are balancing chemical equations. We are thinking about matter. And so we're using those ideas of a balanced chemical equation to help us think about how much of a substance do we need to add to this acidic water to neutralize it, because we want the oysters to survive. And so students use a balanced chemical equation to figure out, I'm going to add this many grams of a substance to water to neutralize it. And then they test it. And they find out that, oh, our math isn't right. The math isn't mathing, and we're missing a key piece here because what we thought we needed to add really didn't do the job. So we go back and reevaluate, and we need to move past just the balanced chemical equation to figure out molar mass and mole ratios. And so this is where we really start to bring in the thinking of stoichiometry as a thing that we need to solve this problem that we have. And students have additional practice built into Unit 4 to do stoichiometry in a phenomenon-based way versus just our, rote memorization and practice that we typically do in thinking of it's a step-by-step process. So let's go to our final slide to wrap up on stoichiometry. Oops. Or did we go? Oh, yeah. So we really use phenomenon to drive why we have to engage in this mathematical and computational thinking around stoichiometry to help us solve problems rather than just presenting it to students as this discrete set of steps. So I think we can hand it off to Michael to talk about our fourth topic, gas laws.
Oh, I love this one because once upon a time I was like, oh, gas laws are great. I love gas laws. I think there's a special place in every teacher's heart for them. But thinking about where we do something related to gas laws, I think is a question we've heard before. And if we check the framework or NGSS, we see some guidance about it, and using those, that is a way to guide our design work. We're going to point out what we do with gas laws and where and why. So I'd say in C1, we're actually doing quite a bit of what I would classify as the fundamental concepts behind gas laws. It's kinetic molecular theory. That's what we have to really understand from a particle perspective if we're ever going to build mathematical models relating how the particle collisions influence other things, like the force against the surface area or pressure. It's in this unit that we're not just talking about states of matter. We think about particles speeding up, slowing down, transferring energy through conduction. transferring matter and energy through convection, thinking about how radiation can be absorbed or re-emitted, all with a model of particles. Particularly think about this for Earth systems related to ice melt and ocean level rises. We got to model solids, ice, and the ground surface below them, liquids, the water, as well as the atmosphere. And that's the opportunity to really start building out a meaningful context for kinetic molecular theory. And we're going to have to reason about changes in volume, changes in density, the number of particles, maybe not pressure, but changes in volume and density at a particle level. We're actually modeling those in middle school a lot. Whether we're trying to explain something like a hailstorm or energy transfer in the context of plate tectonics. So that then sets us up for what we could do if we really want to go to a mathematical model of gas laws. It's not really until the last unit where we're considering, wait, how could chemistry actually help us evaluate what fuels and transportation options would benefit the Earth and our communities in the future? Is the answer batteries? Or is it combustion sometimes? Or fission? I mean, what fuels? Does it matter how much the stuff costs? Or how hard it is to get rid of the products? Well, different communities might have different answers as the technology develops, and it might be different for different vehicles. But it's already in the second lesson of that unit that we would have a meaningful context, a real world phenomena that begs explanation that you could apply relationships of pressure, volume, and temperature to, because the two most common fuels for the vehicles on our road right now are gasoline and diesel. And it turns out, in both of those, we are injecting more particles into a closed system. And then they go through a chemical reaction and the number of particles changes, but so does the temperature. And in some cases, the system self-ignites, like in a diesel engine, when we compress it. And all of it is in service of delivering particle level collisions against the piston wall. That's where we have a meaningful need for explaining why pressure would go up or down in a multi-stroke system of an internal combustion engine. So we give extension opportunities. Say, this is a meaningful time, if it's important to you and your students, the questions they have, to develop a mathematical model for considering the relationship between these variables. In this current context of the unit, it's not necessary for doing the engineering thinking we ask kids to engage in, or to think about the earth science level connections that are behind this global problem that we're going to have to figure out as a world over the next 100 years. So it's not built into the lessons as required, but we do often have extension opportunities to be like, here's a meaningful place to do these relationships because we're in a closed system. Those other things like the first unit, it's an open system, gas laws doesn't make sense to do. They're not applicable. So that's our last example, and we kind of just emphasize on this. If we think like, where's kinetic molecular theory done? Because that's what gas laws are really about. It's like starts in C1, big time in middle school. There is no lot of closed systems to really go further to get to gas laws formally. And it's not explicit in NGSS, so it's not like a disciplinary core idea. But kinetic molecular theory is. So we spend a lot of time reasoning about what's happening at the particle level, well, in every unit of chemistry and many of our middle school units as well. I think that was our last topic. Is that right, Erica? So how could there be more?
Thanks, Michael. Thanks, Nicole. Yeah, there are more. We only talked about 4 today, but we're going to drop a doc in the chat. I'm hoping Nicole will do that for me. We'll drop a doc in the chat, and this is also on our website in our knowledge base that has some of those additional topics. Not in a beautiful presentation with Michael and Nicole speaking to us, but if you'd like to read about some of those other ones and how they're addressed and where, you can review that handout. So to wrap up, one more kind of point that we wanted to cover in our third bullet point at the beginning of our presentation, and this is a big question that we get a lot, especially if we're using OpenSciEd. It looks different from maybe what we're familiar with when teaching chemistry, is we get this question of like, is OpenSciEd chemistry rigorous enough? Is this rigorous for my kids? And with that, I think it's important to really think about what we mean by rigor. And so I'd be curious, like, let me go back to this one. If you have your chat open, maybe drop like, how do you define rigor? Like if you're thinking about making your chemistry course rigorous for your students, what does that mean to you? How would you define that in a sentence or two? And then we'll talk about how we're defining it when we think about OpenSciEd's course. Okay, we got some ideas on there. Constructive struggle, figuring out instead of learning about. Okay, feel free to drop some more ideas. Some ideas that we may mean by rigor, and maybe this is an approach we've heard before or others have had when thinking about rigor, is there's this idea of content heavy rigor. So that might be something where we want to cover many topics quickly. And oftentimes what that leads to is repeat practice and speed. Not saying that those things are necessarily bad, but they can often become what we're relying on if we're trying to get through many topics quickly. So sometimes that might apply in like maybe honors or advanced courses, and maybe that's a way that rigor is being added, is by adding more content or more topics. Another way to think about rigor, and maybe that people maybe don't call it this, but it might be viewed this way if we really step back and look at it, is this idea of gatekeeping rigor. And this is the idea that sometimes it's framed as exclusivity or quote unquote more difficult. So maybe only a subset of students succeed when we frame rigor this way. So maybe it's for advanced learning or gifted or something, but it's a sort of gatekeeping where only the students that can keep up with this are going to be in this rigorous learning environment. And so this reflects like how many of us were taught, but research shows that these don't have lasting understanding, right? If we're emphasizing content, these are also the things that the kinds of tasks that are most easily replaced by AI. So if we're focusing on more topics or more practice, that can be something that's replicated and not authentic for our students in our current world that we live in. And so some other impactful definitions, and I see some of this with connection to some of the things that have been in the chat. Some other definitions for rigor would be three-dimensional rigor. So if we think about the framework and the NGSS, this is integrating those core ideas, the practices, and the cross-cutting concepts. So really developing ideas in meaningful ways and figuring out. And with that, and this is definitely one we saw in the chat, was this productive struggle. So really giving students opportunities to wrestle with challenging problems, right? That's a big evidence of rigor, is if they have to wrestle with something and try and figure it out using their problem-solving skills. A third impactful definition would be access and inclusion. So kind of moving away from that gatekeeping rigor and really thinking about rigor designed for all of our students, not just a select few, and getting all students to where they need to be in order to move on to their next step, whether that's college or something else, but getting them to where they need to be. And then fourth, college preparedness is a really common definition of rigor today that we have and we hear, and that's aligning with what professors expect. And so with that, it's typically reasoning, evidence, and persistence are really some key indicators of that definition for rigor. And thinking about that college preparedness one, a couple of, and these will be linked in the slides if you're interested in these, but a couple of like 5 things that really teachers can influence when preparing students for college and further science learning in college. Depth of conceptual understanding, so really focusing on digging deep rather than rote coverage. 2, engagement in science practices, so really thinking about reasoning and evidence and the skills needed to figure out big ideas. Problem solving and application, so based in phenomena, based in solving problems, a real world approach. 4, math in science reasoning, right? So math preparation predicts success in chemistry and biology when in context, right? So we need to be able to apply our math skills to other scenarios rather than just one specific example or through practice without application to phenomena. 5, study skills and persistence, right? College success does depend on metacognition, study strategies, resilience. So these are 5 areas that we can really impact as teachers if we're thinking about college preparedness rigor. And so how those sort of show up in science and maybe apply to OpenSciEd's chemistry and high school courses is we can explain why reactions happen, not just balancing equations, or apply math flexibly in chemical reasoning, tackling unfamiliar problems and evaluating solutions, thinking experimentally and critiquing experiments, not just following instructions, communicating ideas and arguing from evidence. And hopefully we saw some of these things in the examples that Michael and Nicole shared today and how our students are going to engage with the chemistry ideas in OpenSciEd's course. So in summary, right, kind of summing up all of the different examples in the approach that we see in OpenSciEd and when it comes to rigor, is students are investigating real phenomena, wrestling with challenging problems, building explanations that connect ideas, practices, and math. And we hope, and our goal is that every student, whether they pursue college or not, develop the reasoning, evidence, and persistent skills needed for their future. That's how we're defining rigor in OpenSciEd chemistry. Okay, and so hopefully we saw today that we saw all those traditional examples, or we saw quite a few of those traditional topics, and then we have more to read about for some of the others. And we hope OpenSciEd brings really deeper learning for our kids and rigor for all students. And then of course it's customizable, right? Like we trust teachers to make their decisions and the adjustments that they need to make for their kids, and which is why it's really important. And we hope that this webinar enlightened you to where those things are, so that when you do make customizations to the materials, you can make them with the knowledge you need to make the best decisions for your kids. A couple of quotes, just some from some field test teachers from our high school field tests that we think really like show what rigor sounds like, that definition of rigor that we're applying. Students are more willing to work together as a team to solve a problem or to move our science thinking forward. They're willing to try, willing to make some mistakes, knowing that there's going to be opportunities for revision. So getting at that productive struggle. Students like that there's not one right way at the start. They're willing to put in the struggle and be authentic with each other and give each other feedback. So productive struggle, working together to figure things out. And the physics skills, this is from a physics teacher, they learned are applicable to solving problems in their own community and thinking through the complexities and trade-offs of different solutions. When they aren't given the clear right answer, kids are forced to think more deeply. All right, so let's wrap up. We're really grateful that you chose to spend your evening with us. And we'd love to hear in the chat. These are our 4 questions at the start today. Where are the traditional topics in OpenSciEd chemistry? How is OpenSciEd chemistry different in its approach? And what does rigor mean in OpenSciEd, and how does it show up in the materials? I'd love to hear, like, pick one of those questions. And what is a takeaway from this presentation that you could share with others in response? So if you had like a colleague or someone who asked you one of these questions, what have you now figured out about this that you could share with them? And if you haven't started with OpenSciEd, if you're here just hearing for the first time and looking to hear what we're all about, it's free. You can register on the website and download a unit today. We also have a new library of on-demand support resources, which I'll show on the next slide. So if you want some more asynchronous professional learning and some tools, that is a great resource for you to explore. And then if you haven't already, we have a Facebook community for biology, chemistry, and physics, where there are lots of teachers sharing their experiences and their resources and their ideas. And we encourage you to connect if you're on Facebook with that space. We'll drop this link in the chat. I know we've shared a lot of links, but you can also just go to the website and search for on-demand library. But on there, you'll see lots of different tools that you could review and utilize in your classroom and to prepare and plan for lessons and teaching. That's it. Our emails are up there on the slide. If you have any questions, we encourage you to reach out. And thank you for joining us this evening.